So we got some homework coming up for Wednesday. So we got a couple of these biaxial ones, and we got a couple ones that involve power and whatnot. There's 4 of them. So we got any questions on this one? On this one, I think what you want to do here is, as you know, most commonly you always want to do, you want to find that polar moment of inertia. And that's 1.27 times 10 to the minus 6, and that's meters to the 4. Generally speaking, on these torsion problems, you always want to do that. All right, and then what you want to do is you want to find tau max, okay? And that's going to be 1.89 megapascals. Now, what you want to do next is you want to assume there's a little bit of an element here, okay, like that. And you want to look at what's going on with that. Now, what's happening here is if you twist the front end of the shaft like that, you're going to get a reactive torsion coming back the other way. And based on that, you should be able to come up with the torsion on that element. Okay, so you're going to have that element like so, and then you're going to have the one of those torsions acting and the other torsion on the other side, and then of course you'll have the other two. So you should be able to come up with a torsion diagram. Keep in mind that when you do that, sigma x and sigma y are 0, okay, biaxially. There's no normal stress in the x or y directions. Okay. So once you have that, then what you want to do is just throw the equations at it to find the stress on that line. What you're looking at is a line that is in here, kind of runs like that. That's AB. Now keep in mind that theta for that plane is not equal to 28 degrees, right? Because that's not referenced on the proper line. So don't plug 28 degrees into the formula. That's not the angle to use. All right, and then what you're going to want to do is just go ahead and find tau x1, y1 and sigma x1. Okay, tau x1, y1 will be positive 1.05 megapascals. And sigma x1 will be positive 1.57 megapascals. Okay. I mean, that's basically the thing on that. You are going to want to pay some attention here to this sketch. You're going to want to find the direction of the arrows on these. Okay. Okay, so that's kind of the drill with that one. Any questions on it? You know, if you have the concepts on that one, that's pretty straight up. Both of these are. There's not a whole lot of calcs with them. We good with that? Okay. The next one is kind of like that, but a little bit, you might say, backwards of that. What you have here is that this seam here can handle 1,400 pounds per square inch. Okay, that's the maximum normal stress. Okay, so if that normal stress is 1,400 psi, what's the biggest torsion that you can apply? So you want to find the moment of inertia. You always want to do that. So that's 517 inches to the 4. And then you're going to want to work with a couple equations. The first one just says that sigma x1 is tau xy times sine of 2 theta. Okay, now once again, I'm trying to get you used to all this. This is why I keep doing this. Theta is not equal to 75 on this one. Okay, it's not. So just always reference the angle to a plane when you're doing stress in the vertical. That's always how you reference that, okay? Regardless of how the angle is presented. So what you're going to have is sigma x1 is tau xy sine 2 theta. So you're going to solve that for tau xy is what you'll do on that. And that ought to be 2,800 pounds per inch squared. And actually that's minus is really what it is, because when you look at that, you're going to get a, well, when you look at the shear on that, it's going to come out to be negative. Okay. And then the other thing you've got here is that tau max is TR over I, and solve that for T. And you should get, just depends on how you look at it. I got 321,000. I guess I took this one out quite a ways, 689 pound inches. A little bit of overkill on the significant figures there, but that's the idea. Okay. Questions on that? So that's that one. Okay, from there we get into these power type problems. Now power just fits right into torsion on these next ones. The kind of the transition, or the way you get from one to the other, is you just use the fact that power is torsion times omega, okay? Omega in radians per second, so be careful on that. What you've got here is 1 revolution is 2 pi radians, okay? And 1 RPM, what that is 1 revolution, which is the turn of a circle per minute. So you got to be a little careful on your units, and that is the general kind of thing with torsion, is the units come up a lot. Okay. So we all right with that? Okay. All right, now this first one here, you got a few things to do. You got 125 horsepower, but you want to get that into the native units, or the more usable units, whatever you want to call them. There we go. So this first one here, we've got these different parameters here that govern the shaft. This is the different stresses you can handle up there. Based on that, you want to find how big of a shaft you need. Okay. So you start by kind of working through the units, and you can see I'm doing that with 3 of them there. I'm getting the power in inch-pounds per second. I'm getting the revolutions per minute in radians per second. And then I'm going to get the angle in radians. It's 0.03054. So you want to do all the conversions to get that set up. Often I tell you to find I, but you don't have I here, because I depends on the size of the shaft. You're going to figure out how the size of the shaft, so you don't have I. So you convert the power, the angular speed, and the angle into the appropriate units. All right, now you know that the power is the torsion times omega. You've got omega and you got the power, so you can solve for the torsion. It's 13,130. Okay. So that's just a little bit of an extra step there to find the torsion. So we doing all right with that? Any questions? Okay. All right. From there, it's just a matter of taking those two equations, one for the shear and normal stress. See, the formula for tau max and sigma max is the same. It's TR over I. You just go ahead and solve those for the radius. Now that, to do that, you have to know that I is pi over 2 R4. Okay. So if you take TR over I, that reduces down to 2T over pi R3. Solve it for R, you get the third root of the 2 times the torsion times pi over either sigma max or tau max, okay? And you've got all those things, okay? You've got the torsion, you just found the torsion that's applied, you've got sigma max and tau max. You can plug that in and you'll find these different required shaft radii is what they are. Okay, so the first one is required to prevent tau max from going over its allowable limit, which is 14,000 psi. And the second one, when I plug that in, that is the required shaft radius to prevent the normal stress from going over 22,000 psi. Okay. So we all right with that? All right. And then the last thing to do is to check the angle. Okay. So you can do the same sort of thing with that phi formula. Phi is TL over IG. You know, understand that I is pi over 2R4. Rearrange that and take the fourth root. You solve for the radius, the fourth root of 2TL over pi phi g. You got all that stuff to plug in. You got the allowable angle, and you get a third required size for the shaft. So these are 3 separate things to look at. You solve for the shaft size for each one of the 3. And then you've got 3 different shaft sizes now that are required. Each one is the minimum or absolute required shaft size for the different thing you're analyzing. So what that means is you pick the biggest, right? Because when you do design, you pick the lowest load, because that's the safest load. You pick the biggest size, because that's the safest size. So you pick the biggest one, double it, because you solve for radius, but you spec shafts and other round things, you spec them on diameter. So 1.9 inches. We'll leave that at 1.9 inches when you start working. If you haven't already, my guess is you would probably go with a 2-inch shaft. I mean, you know, when you start, you know, there's all different levels of design on things. Normally, like a mechanical engineer is going to pick a shaft for a usage like that. It's like you're going to custom mill one. You know, maybe for a one-time use you might, but you know, for something like this with a motor and all that, probably gonna go with a 2-inch shaft. Right. But we'll call it 1.9, just, you know, to look at it that way. Right. So we good with that one? We got any questions on that one? Okay. All right. Okay, the one after that, you've got the shaft spinning at a constant 90 RPM, lifts the mass shown, find the torsion and power developed by the shaft, the maximum shear and maximum normal stress in the shaft. All right, this is just running through the basic equations. Again, as this class, as you often find, it's, you know, putting them all together, I guess, you know, is the thing. So, all right, now that's a mass. Don't want masses, I want a weight, okay? So that's going to be 2747 newtons. Okay, be the first thing I do. All right, now the torsion then, you got to find what that is. That's lifting the weight. It's a constant angular speed, which means you're not accelerating that weight. You're lifting it at a constant velocity. So I think when you put all that together, you're going to get the torsion as 124 Newton meters. Now be sure you can get that figured up. I gave you the shaft dimensions. I also, it's not on this sketch, but on yours you've got the pulley dimension too. It's a 9 centimeter pulley. Okay. So you want to kind of analyze that, look at the weight, and look at the moment that it causes about the center of the shaft, and that should get you the torsion. Okay. Find omega, and again, you got to watch your units on this torsion stuff. It just seems to be something that comes up a lot. All right. Now, once you've got that, you should be able to come up with the power. It's going to be whatever you got for the torsion times omega, and that's going to be 1165 Newton meters per second. There we go. It's a watt, I think. And then the last little bit here is you got tau max and sigma max. They're equal to each other. They're TR over I. And that's going to be 3.11 megapascals for that. There is kind of an implied plus or minus on these. So, yeah. But I'll just call it 3.11 megapascals. So we're doing all right with that? All right. So that's the deal with that. So that's just due Wednesday. Okay. Other questions on the homework? Yes.
Why isn't the answer very different
That's for this slide. I think this is an old slide, and I think I changed stuff around on yours. I think. Let's check and see. Yeah, I'm not sure. Yeah, mine are different, and I think I don't think the I think this slide is based on an old problem. I think the pulley size I changed. If you look at the answers in your book, I bet they're different than what I have up on the slide. Be my guess. It's worth a look. I'm not. So we're just talking, for those of you online, there's a little discrepancy between the answers I'm getting here and the answers in the box, and I think the problem is that the answers in the box are old and were based on a different pulley size. That's kind of what I remember. Yeah, it looks like the 303 has been changed, right? So, good? Okay, so yeah, I think we're all right. Just this is an old problem with old answers. Those are no good there, but the ones in the book seem to be good. All right, okay. Other questions?